Stripping down science. The Naked Scientists.
Hello, welcome to this week's edition of The Naked Scientists with me, Chris Smith, and also with Kat Arney. Hello, Kat.
Hello.
Now, coming up this week, we've heard of solar cells, but now scientists have made the world's smallest examples of them. They're solar-powered nanowires. They're absolutely tiny. They're just 200 times thinner than a human hair, so absolutely microscopic. How do they work? Well, we'll be finding out shortly. Also, we'll be hearing how researchers have used a chemical which is normally found in the brain to produce a glue that's so sticky that it'll even bind to Teflon. So what can we do with it? And also, how scientists have discovered how the human body combats viruses, and in particular, hepatitis C. That's all on the way.
Also this week, we are delving into particle physics, including paying a visit to the Diamond Synchrotron in Oxford. That's the most expensive diamond I think we'll ever get near to. And this is helping scientists to solve the mystery of the Dead Sea Scrolls, those ancient parchments that go back thousands of years, but are actually too delicate to even unroll.
We can take lots and lots of pictures at different angles of a piece of parchment, and we can then reconstruct on a computer what the original object was. And that's where we've begun to realise that we can read objects which we really would not be able to unroll.
Plus, we're going to be joined by physicists Ben Alanak and Christina Lazzaroni to find out what's inside an atom and how the Large Hadron Collider at CERN is going to help us find out.
And sticking with the hard stuff, in this week's Question of the Week, we're also solving this cooking-related conundrum.
Why is it that chocolate chips in cookies melt if you touch them, but they survive the baking process?
Absolutely intriguing, and the answer is definitely going to surprise you. It's coming up later in the programme.
And also we'll be eating all the chocolate biscuits. So if you have a science question for us about particle physics, what makes up the universe, what it's all about, or if you just want to say hello, do get in touch. Email chris@thenakedscientist.com.
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider, on the web at ukfast.net.
And we mentioned this very interesting study looking at the world's smallest solar cells, and now scientists have really taken it to another dimension quite literally, because Charles Lieber and his colleagues there in Harvard University over in the US have made solar-powered nanowires. So they've taken all of the ingredients of a normal flat solar cell and found a way of rolling them up to make the equivalent of a tiny cable. And the way it works is that the inside of this tiny cable, which is just 300 nanometers across, that's 200 times thinner than a human hair, consists of silicon, which is the stuff you find in computer chips, to which someone has added a small amount of boron, and boron has got lots of electrons to give away. And they've coated around the boron a layer of pure silicon via depositing the silicon in this clever vapour deposition process, and then the outside of the wire has another layer of silicon, but this one's got some phosphorus mixed with it, which likes to soak up electrons. And the way it works, when some light in the form of a photon of energy comes in, it lands on the inside part of the wire where the boron is, knocks some electrons off the boron, they go into the outer layer of the wire where the phosphorus is, and they can't get back because of this intermediate insulating layer of silicon. So they flow around the circuit, do some work, and then come back to where they started. And although they're not very efficient at the moment, they're just 3% efficient, and that's a lot less than the best solar cells we have at the moment, which can be up to 30% efficient. The team are hoping they'll be able to get them up to about 15% before too long.
So what do you reckon you could do with these?
Well, they're not terribly powerful. They make between 50 and 200 picowatts. In other words,
that's not going to fire your telly, is it?
No, it's less than a billionth of a watt per wire. But what they have shown is you can connect them together either in series, so you can add up the voltage from each one, or in parallel, so you can multiply the current from each one, and this increases the output. Or if you shine brighter light on them, and they've done this with using light which is about 8 times brighter than sunlight, then you can power things, and they managed to power a nano-powered pH detector, in other words, something that can register how acid or alkaline something is using this. And so, as Charles Lieber says, this enables us to study a fundamentally different geometry for photovoltaic cells. We're no longer constrained and confined to the old way of doing it. You can start to make them in a new shape and therefore build things at a very, very small level, which light can power, without having to have macro things to power it.
That sounds absolutely genius. Completely on the other end of the scale, almost. Mussels. Mussels live in the sea. I like eating them. And as well as making a tasty meal, mussels have actually provided the inspiration for a new generation of polymers. Mussels can attach to virtually any surface, including things like Teflon, which is allegedly completely non-stick. And they do this by producing molecules called amino acids that form strong bonds with the surface that the mussel's sitting on. And one of these amino acids is dopamine, and that's a chemical that's usually used to send signals within our brains and brains of other animals.
It's the brain's pleasure chemical, isn't it?
Exactly. But mussels use it as a sticky chemical. because they don't have brains. I guess they've got to do something with it. Anyway, writing in this week's edition of the journal Science, researchers led by Philip Messersmith have taken a tip from these clever bivalves, and they use dopamine to form thin films on surfaces like metals, glass and ceramics. And the technique simply involves you dip your surface in a solution of dopamine at the same acidity level as seawater, and it spontaneously forms a thin polymer layer after a couple of hours. And then you can use this film to attach other chemicals and other molecules onto your original surface.
So what sorts of things are they sticking to, and what can they stick with?
Well, you actually use this for metal plating. You can stick metals onto plastic. So, for example, you could build up a flexible plastic metal-plated thing. So you could use that for flexible electrical components. Or you can develop paints that don't pick up dirt because they're non-stick. And also, you can actually attract biological molecules with this dopamine coating. So you could actually make medical implants that maybe kill bacteria or release chemicals.
It sounds really interesting, because the concept of being able to electroplate plastic and just make electrically conductive plastic in itself is amazing, because you can think of all of the things you could make. At the moment, you have to use very complicated to work with materials to make conducting surfaces
Electric
and microchips
trousers,
and things.
all sorts of things.
Well, yeah, PVC,
That's what
conductive
I want.
PVC. That would be good in your book.
Electric trousers, yeah.
Well, anyway, sticking with very small, scientists have actually uncovered a very exciting mechanism by which the body spits out and gets rid of viruses. Now, the group of researchers in particular, they're led by Michael David, he's at UCSD over in the States, have been looking at hepatitis C. Now, hepatitis C is a major problem. It affects about 1% of the population of the Western world, but it can be as high as 10% of the population in some countries. And why it's a problem is it's a blood-borne virus, so needle sharing, blood transfusions, if you have needle stick injuries and ear piercings even can spread it. Once you've got it, about 80% of the time it becomes chronic. That is, you can have it for a very long time. And in the course of having this chronic infection, it continuously injures the liver and can cause cirrhosis.
Can lead to cancer as well.
It can cause cancer in about 5% of people who have it. And Anita Roddick famously caught it from a blood transfusion. And Pamela Anderson has also said to have had this, and she reckons she caught it from a tattoo needle. So it can be caught. It is common. It is out there. We know from medicine now that about half of people who have it, if they're given one of the body's own signalling hormones called interferon in high doses, in 6 months you can cure about 50% of people. They'll clear the virus. But no one has a clue how it works. And so this research group decided to try and solve the puzzle. And they wondered whether it could be down to a thing that's recently been discovered, which is a phenomenon called microRNAs. Now, inside each of our cells is obviously the DNA, which has got our genes written into it, but also in the cells is a small population of nucleic acids called microRNAs. And these are very short sequences of genetic material, and unlike DNA, which is 2 chains stuck together, these are just one single chain. And what they do is cruise around inside the cell, and if they come across another message, a genetic message which is the mirror image of theirs, they can lock onto it and inactivate it. So what the researchers wondered was whether interferon switches on some of these microRNAs that then are complementary or inactivate hepatitis C.
And do they?
So, well, that's what they did. They got some cells in the dish, put a lot of interferon onto the cells, and then looked which of their microRNAs were turned on. And they found about 30 microRNAs that had very high levels after they did this. And then when they compared the sequences, the genetic sequence of those microRNAs with the genetic sequence of hepatitis C, 8 of them were an exact match. So this suggests that what's happening in cells that have been infected with hepatitis C in a person, when you give them interferon, it pushes up the levels of these things in their body, and this turns down the level of hepatitis C. And to prove that, they infected some cells with hepatitis C in a dish. They then added synthetic versions of these microRNAs, and they were able to reduce the level of hep C by 70% in the dish. And so this gives us a whole new bunch of targets to try and aim at, to try and treat hepatitis C in future. So not only have they solved how interferon works, which we never knew before, may also help us solve a major problem that causes liver disease.
That's really interesting, because there's just starting to come through in clinical trials, actually, this kind of RNA-type treatments. It's still very early stage, but potentially that kind of thing is really exciting, potentially treatments for humans. Anyway, it's become traditional that Dr. Chris nips to the little boys' room 5 minutes before every show, all the time.
No comment.
It's true, but scientists in Belgium have found a gene that actually may be partly responsible for his urge to go and spend a penny. Normally, when our bladder gets full, then this sends signals to the muscles around it, telling them to contract, meaning that you have to go to the toilet. Now, Bernd Nilius and his team have found out that a gene called TRPV4 is faulty in mice. And when it's faulty, they become incontinent. And this means that they no longer have this level of control over their bladder muscles, and so they just kind of go all the time. And the researchers looked at bladders taken from mice with the faulty gene and found that they sent sort of smaller chemical signals that tell the muscles to contract, compared with bladders from mice with an intact version of the gene. So kind of they're not sending the signal that the bladder's full, and instead you've just got it leaking all the time.
So is this relevant to humans who have incontinence problems?
Well, they think it is. Now, TRPV4 gene, it makes a protein that sits in the wall of cells that line the bladder and sends signals to the bladder that tells the muscles to contract. And the researchers think that this has a really important role in translating these signals that allow a controlled trip to the loo. And although these are just experiments in mice, there's the possibility that in humans it could be a good target for people who maybe have incontinence problems, so potentially for drugs or that kind of therapy in the future.
Well, let's hope so, because it's pretty miserable if you do suffer with that. So
Exactly.
Let's hope that they do make some progress in that direction. Now, to finish off this week, I would make some joke about wetness and marine environments, but it seems a bit tasteless. But researchers have actually made a major breakthrough in solving a big mystery of the sea, which is coral spawning.
Oh yeah, they all do it at once.
That's right. If you watch David Attenborough, you'll have seen this phenomenon where on 1 or 2 days of a year, every single coral in a whole reef will decide this is the time to spawn.
Like a mass orgy of coral.
And they also wait until it's a full moon. Now, how do they know that it's time to do this, and how do they know that it's a full moon? And that was the question that occurred to a bunch of scientists at the University of Queensland, and Oren Levy is the first author on a paper in this week's Science. And they went out to the reef, collected some samples of just reef-building coral. It's called Acropora millipora. And they decided to use the genes that make body clocks in humans and flies and worms, and use that gene to see if coral had its own version of that gene. So they looked for the human and worm and fly equivalent in coral, and they found it. It's a gene called Cry1, and they found another one called Cry2, and that's short for cryptochromes. And cryptochromes are genes that make proteins that can detect light. They detect blue-green light. And so to see if this was relevant, they went out to the reef and they looked at corals when there was a full moon and when there was no moon, and they found that these genes were following the moon cycle, and particularly Cry2, the second of the two genes, was very, very high levels when there was a full moon, but not when there was no moon. And to check that they were on the right lines, they grew some of the coral in the lab, and they turned the light on for 12 hours, turned it off for 12 hours, on for 12 hours, off for 12 hours, did that for a long time, and looked at these gene levels, and they definitely came up when the light was on, and they went down when the light was off. And then they kept the coral in the dark for a while, and the genes went away. So it looks like this is part of the way in which the coral detects that it's light, that it's a moonlit night, and Cry2, second of the two genes, seems to be linked to how the coral knows what the time is, and therefore it's potentially time to spawn. There's a lot more to find out yet, which is how they all signal that all of them have got to do it together. But at the same time, very exciting, because it's the first sort of insight into how coral has this clock.
Amazing. Everything from corals to wee to nanotubes on The Naked Scientists. Later on, we're going to be talking about particle physics, all things delving into the nature of matter. If you have any questions for us, email us chris@thenakedscientists.com.
Thank you, Kat. Now, it's quite unlikely you're going to get the chance to conduct your own experiments with the Large Hadron Collider, which is what we're going to be talking about this week. In fact, with any particle accelerator at all, because they're quite hard to come by and quite expensive. But as long as you've got an old-style TV or a computer monitor, and we don't mean the flat-screen, expensive LCD ones, then you're in business, because Ben and Dave have come up with a particle physics experiment that you can do in your living room.
Hello, welcome to this week's Kitchen Science. Now, I never thought I'd be saying this, but today I'm going to do a particle physics experiment. This is really exciting. I've got Dave Ansell with me, of course.
Hi there.
And this week, to help me out with my particle physics experiment, I have three girls from the 23rd Cambridge Brownies.
Hi.
And what are your names?
Ella S, Ella T, Poppy.
Now, do you know anything about particle physics? Have you ever heard of it?
No.
Have you any idea what it might be about?
No.
So, Dave, clearly this is going to go over their heads, or is it something that they can try out?
It's something really simple to do, although I wouldn't suggest it doing it on a TV which you like at all. It may damage it.
So we've got my old monitor here today because I don't really care if it does get broken. I'm planning on recycling it soon anyway. So what is it that we're going to do with a computer monitor?
We're going to do two things. One of them is just turn it upside down and see if that has any effect on it. The second one is take a magnet and put it near it and see what that does to the picture.
OK, girls, now what do you think will happen if you turn a TV or a computer monitor upside down?
It will go blurry and the picture will be upside down.
Like if you watch a TV closely, there's sort of like green bits and red bits to make up the thing, I think it might go a bit like that.
The picture will just stay as it is, or it will go all fuzzy.
And the other thing Dave said that we're going to do is we're going to put a magnet near it. Now, do you think a magnet would affect a TV?
I think the screen will go fuzzy again.
Okay, have another blurred screen. And what do you think will happen?
I think it'll go all weird.
Well, we've already said that we shouldn't do this with a TV that you're attached to or one that you rely on. So, Dave, if people want to take the risk, can they do this at home?
There's no particular reason not to. You'll need one of the old-fashioned cathode ray tube TVs. These are the long, deep ones, not the modern flat screens, like a plasma or an LCD. So old-fashioned TV, and it should be fine.
So if you do have an old CRT-style TV at home that you don't really care about too much, give this a try. Turn it upside down while it's on, see what happens, or wave a magnet at the screen and let us know if anything interesting happens. We'll catch up with you later on in the show to let you know what happens to my old monitor.
And it is pretty cool, I promise you. This is The Naked Scientists with Chris and Kat. Thank you to Ben and Dave there. We'll be rejoining them later to find out exactly what happens. So if you want to do it, get your old television and get a magnet, turn the TV on, and then have a little bit of a fun with the magnet near the screen.
We've got an email in here from Dave Levick from Australia, and he says, "Hi Chris and team, myself and my partner are currently on a year-long cycling tour around South America, and we download your podcast regularly and listen to it in our tents."
Yes, I have to apologise to him for that, because he sent me that earlier this year,
Chris.
and I lost it down the back of my cupboard, and I had intended to read it out, so I'm very sorry about that. But I hope you're enjoying your cycling tour, and you've made it back to Australia or not so far.
Also, we've had a question just in from Mark in Bletchley, and he wants to know, do astronauts change their diet before they head off into space? Chris, what do you reckon?
Well, we covered this on The Naked Scientists a couple of 2 or 3 months ago in a limited sense, and in the early days, people did worry about astronauts' diets and going into space for various reasons. One is that if you have gut flora, bacteria in your guts that make a lot of gas, and then you eat foods that they like breaking down and turning into gas, then there's a worry that you could end up making a lot of gas, and that could be quite unpleasant inside your spacesuit. That was the theory. So diets were carefully selected to be what we call low residue, and also to be fairly stomach kind.
So no beans.
Yeah, so they tended to avoid those kind of fibre-rich foods. But in fact, experience has shown after many, many space missions that that's probably not necessary. So they just go for whatever you can desiccate down to dried out astronaut food. There's not really any benefit to doing that, as they've subsequently found out.
Lovely.
Interesting one here from Neil Gibson for you, Kat. Says, "Hi guys, great podcast, but I've been watching Michael Palin making his way around Europe on the BBC, including Estonians firewalking. What's the science behind firewalking? Why don't they burn their feet, or is it a trick or something?"
Well, there's no trick to it necessarily. What it is that it doesn't look. It's not entirely what it looks like. Basically, there's three components.
Looks pretty hot to me, Kat.
It does look hot, but there's 3 components to this. The first thing is that when you're walking across fire, understandably, you do it a bit quickly. So you're actually minimising the time that any particular part of your body is in contact with the fire. This is the same reason that lizards scoot about in the desert on hot rocks. The quicker they move, the less they're actually going to burn themselves. And there's 2 other things. The fires are lit and then they're let to burn and sort of basically become barbecue. But the top layer of that is ash. And ash is actually a pretty good insulator against the direct heat underneath. So you can feel the heat above it, but actually the burning heat won't get through so much. And also carbon is the component of the coals. And carbon's actually a very poor conductor of heat. So heat that's burning right at the bottom of the fire pit won't come up so much. So it's not as hot as it looks. And also you go across it very fast.
And one theory I heard was that because you're a bit nervous, in the same way as you get sweaty hands when you're nervous, your feet sweat a bit, and you effectively surf across the coals on a cushion of steam, which also helps to keep the temperature down. Do you believe that?
Yeah, I think that sounds plausible. Maybe we should get Dave to do it. It's kitchen science. We have another question for Chris. And this is from David Stock. And it's, Chris, when a person has spinal damage that leads to paralysis and the loss of feeling, is the loss of feeling that they get the reason for the paralysis, i.e. the brain can't feel your limb so you can't move it? Or is it the other way around? What's going on?
It can be both, because the spinal cord isn't just a one-way street. It's got information coming out of the brain down to what we call motor neurons. They're the motor nerves that supply your muscles, and at the same time there's information coming in from the body, going up the spinal cord to your brain, telling your brain where your body is in space, how fast different muscle groups are moving, and where they are, and whether the movement you've just made has been completed. So if you damage the spinal cord, you can damage just the sensory fibres, and that means you can't feel your body, but you could potentially still move. You can damage just the motor fibres, fibres, which means although you can feel your body, you can't make any movements. But more usually, because it's impossible to be that discrete and the spinal cord is so specialised, when you make a lesion in the spinal cord, such as people who dive into swimming pools where it's too shallow and they impact on their neck, they break their neck and this severs the spinal cord and it disjoints all of the fibres coming up from the body, telling the brain what your body's doing, what it feels like, as well as the fibres coming down out of the brain that tell your muscles to move. So you neither can feel your body nor actually make it move. So very unpleasant.
Doesn't sound nice at all. Anyway, you're listening to The Naked Scientists, and we're going to take your calls on particle physics and anything to do with the universe and structure of matter, because we have two absolutely fantastic guests coming into the studio. We have Ben Alanak and Christina Lazzaroni. So email chris@thenakedscientists.com.
The Naked Scientist Podcast, brought to you by thenakedscientist.com.
It is The Naked Scientists with Dr. Chris and Dr. Kat, and we are going to be probing the origins of the universe and the structure of matter. What's inside atoms, that kind of thing, coming up in a moment on the programme. But first, earlier this week, Her Majesty the Queen and His Royal Highness the Duke of Edinburgh officially opened the Diamond Synchrotron, and that's in Oxfordshire. Now, this very expensive device creates high-energy electromagnetic radiation. That's known as synchrotronic light, and it's filtered to give you an extremely intense X-ray beam, which is hundreds of times more powerful than the one that you'd get in hospital, thank God. Now, we sent Mira down to the site this week to find out how it works, and also the benefits of using such high-energy light.
Hello, this week I'm at Diamond Light Source out in Didcot, Oxfordshire, to find out about the giant particle accelerator located here, known as a synchrotron. Now, the building itself is a huge silver donut-shaped building, and to give you an idea of just how big it is, it apparently covers the area of 5 football pitches. But what I'm here to find out, really, is what is a synchrotron, what does it actually do, and how does it work? I'm also going to be finding out just how this technology is being used to benefit everyday life, and even to uncover the unknown messages contained in ancient parchments such as the Dead Sea Scrolls. To answer the first few of my questions is Richard Walker, who's the technical director here at Diamond Light Source, and we're actually inside the synchrotron now. So what exactly is a synchrotron?
Well, a synchrotron, as you rightly said, is a particle accelerator. In the case of Diamond, we accelerate electrons. We accelerate these in a large circular machine, about 0.5 kilometre in circumference, where they reach a very high energy. The energy is 3,000 million volts. And at that energy, they give off very large quantities of electromagnetic radiation when they're bent to maintain their circular orbit. And it is this electromagnetic energy, this electromagnetic waves, which is called synchrotron light, that we use in the experiments.
So we're actually inside the synchrotron itself now, so where are we standing?
Well, we're actually stood in the linear accelerator, which is the first part of the acceleration system. Right at the beginning, where the electrons, if you like, come to life, they are liberated from the atoms in an electron gun. This electron gun fires the electrons into the linear accelerator, where they're accelerated up to 100 million volts. And then from there, they're transferred into another synchrotron, the booster synchrotron, where they're accelerated up to the final energy of 3,000 million volts before they're injected into the storage ring.
So they're bent round, and this is done so using magnets?
We use a large array of electromagnets, both to bend the electrons to form the circular orbit, but also to focus them and keep them very tightly compressed, because it's the small size of the electron beam which gives rise to very bright synchrotron light that we want to generate and use in our experiments.
So now I know how the synchrotron actually runs, but what benefit does this high beam of light actually provide? I'm with Sanjeet Desi, who's a principal beamline scientist here at Diamond. What exactly is a beamline?
A beamline is a series of X-ray optics that helps channel the light that's produced in the machine all the way down to the sample, where we have an electron microscope that we use to study anything from magnetism to chemical reactions on a surface.
So we're outside your nanoscience beamline now. So what is this that we have in front of us? How is this light being channeled?
If you take light into a camera, you use a series of lenses to focus the light onto your film. If you try to do that with X-rays, the X-rays just go straight through the lens. So instead of using lenses, you have to use mirrors. So the beamline is actually a series of half a dozen mirrors that take the light and channel the light and focus the light down to our sample, where the light is only a tenth of the width of your hair, but it has about 1,000 billion times the intensity of a hospital X-ray source.
How many beamlines are there actually here at Diamond?
Well, in phase 1 of Diamond, there were 7 beamlines that were constructed. You can do anything on a beamline, from looking at the structure of a protein to understand how a virus attacks your body, to looking at structures under extremely high pressure and extremely high temperatures. And that's, for instance, important for understanding how iron behaves at the Earth's core. So there's a whole host of ways that X-rays interact with matter to work out exactly what's happening in materials at the fundamental level of the atomic scale.
So extremely variable fields of science are being explored using this synchrotron light. But it's not only science that's benefiting. Scientists are also trying to understand more about history. Professor Tim West and his team at Cardiff University have been using synchrotron light to research the structure and text of ancient parchments, such as the Dead Sea Scrolls, potentially enabling them to read the scrolls without even having to unravel them. I've got Tim here with me now. Hello, Tim.
Hello, Mira.
What made you start working with ancient parchments?
Well, what a lot of people don't know is that parchment's actually made out of skin, dried skin, and therefore that's made out of collagen. And I've been working using synchrotron radiation to understand the structure of collagen for about the last 20 years. What we've been trying to do is to see how intact the collagen is in a piece of parchment, because what happens to collagen is, as it gets older and the control mechanisms of repair are lost when we're looking at something which is no longer in an animal, we begin to see that the collagen deteriorates into gelatin. Collagen is really like a little rope-like molecule which really gives us strength in all of our tissues, our tendon, our bones and our skin. And when it deteriorates into gelatin, usually in our body it's taken away and recycled, but in a document like a historical parchment document, the gelatin just sits there. It's lost its strength. It likes to take up water in the way that gelatin actually is a jelly, and therefore the parchment becomes very, very fragile, brittle, and very, very difficult to unfold and read and handle.
So how are you using synchrotron light to overcome this problem?
Well, first of all, we can begin to detect, without hopefully damaging a piece of parchment, how intact it is. Using the synchrotron, we have a very fine beam of X-rays we put through the parchment sample. The way that the X-rays interact with the matter tell us about the state of the matter that's present. We get a very distinct signal of the way the X-rays are scattered for collagen and a different one for gelatin. And we can begin to tell the difference between those two and then advise on what we call the collagen to gelatin ratio is in any of these samples. We have looked at the Dead Sea Scrolls here using the scattering to try to understand about the damage that's occurred to the Dead Sea Scrolls, because what we're finding is that the caves that the different samples were coming from seems to have affected how stable they are and how they've managed to stay intact. When we find that a sample is possibly so damaged that we really think that it shouldn't be displayed or unfurled, there's a second approach with the synchrotron that we can begin to use, which really relates to a process called tomography. If we pass an X-ray beam through an object, then the picture that we get depends on presence of things like writing on the surface of the parchment. So from that, we can take lots and lots of pictures at different angles of a piece of parchment, whether it's a rolled up piece of parchment as a scroll, and we can then reconstruct on a computer from all the different absorption patterns that we have what the original object was. And that's where we've begun to realise that using the ink on parchment and the surface of a parchment, we can read objects which we really would not be able to unroll.
So there you have it, irony at its best. This giant silver donut is enabling scientists to probe matter down to tiny atomic scales, and this extremely new technology is going to provide the answers to questions and beliefs that go back thousands of years.
Donuts. I'm sure there's plenty of people out there who do want to know the actual contents of the Dead Sea Scrolls, but I guess the next issue will be getting hold of them all. That was Mira Senthilingam reporting from the Diamond Light Source. That's the new synchrotron in South Oxfordshire, which was officially opened on Friday.
And this is, of course, The Naked Scientists with Dr. Chris and Dr. Kat. And we're looking at the origins of the universe, what's inside matter, what are atoms made of this week. And we've got two wonderful guests with us. One of them is Ben Allanach. He is a theoretical physicist from the University of Cambridge. And we've also got Christina Lazzaroni. She's in Birmingham University. But let's kick off, first of all, by talking to Ben. So when we're talking about atoms, I think the ancient Greeks, going back sort of Democritus time, had a concept of the atom as this tiny particle which you link lots of them together and got something. But how do we actually know what's inside them?
100 years ago, Ernest Rutherford, down in the Cavendish lab here in Cambridge, he fired radioactive particles into atoms, and you can tell from that, roughly speaking, what's going on inside. One in about every 8,000 of these particles came back at him, and he measured those with a Geiger counter. And that led him to completely throw away the model at the time, which was a plum pudding model of, some sort of squishy stuff, which was positive with little electrons dotted around it. What he realised was, actually, most of the atoms is empty space with light electrons flying around the outside. And inside there's a very small, hard, dense core called a nucleus.
It's interesting you say about the empty space, Ben. I've got an email here from Jack Dowd, who says, "Hi guys, I'm listening to you in Brooklyn, New York, and I like your programme. I've heard there's a huge, vast amount of empty space between the orbiting electrons and the nucleus of an atom, and I've been told that if all the empty space was taken away so that every single electron touched another electron and the nucleus, then the size of the world would theoretically be the size of a melon."
That could actually be true. I'd have to do a calculation on the back of an envelope to be absolutely sure, but it is a huge amount of space, and the particles inside are tiny.
But what are the actual particles that make up an atom?
Yeah, so around the outside you have electrons. They're light, negatively charged, electrically charged particles, and inside you have the nucleus, which is made up of protons and neutrons. They're kind of heavier stuff that stick together quite well.
And how big actually are these things?
So an atom is roughly 10 to the minus 10 metres, so that's a tenth of a billionth of a metre across, and the tiny constituents in the middle are kind of almost a million times smaller than that. So they're just unimaginably tiny, really. And
the nucleus is positively charged because it's got the protons in it, and the electrons are negatively charged. Now, I can understand why the electrons would be clung onto by the positive core of each atom, the nucleus, but why is it that all those protons with that big positive charge can be stuffed together and they stay there? They don't all fly apart?
There is an additional force keeping them together. That's called the strong nuclear force, which is, they're in there, they're stuck in there with neutrons as well, and this thing kind of just sticks them together, basically.
And so how do we actually work out what the different atoms are? Because if I've got an atom of, say, oxygen, which I'm breathing, how is that different from an atom of, say, the carbon that I'm burning to make the energy in my body?
Yeah, well, you can weigh that. I mean, through indirect means you can weigh them, and you can work it out through chemical reactions and so on, to work out how many of the different atoms make different substances up.
And delving a bit more deeper into the structure of matter, I mean, you hear about things like quarks and neutrinos and all these kind of things. How do they fit in, and how do we know that they're there?
Well, as far as we know, they're the smallest bits of matter. So if we go deeper into the nucleus, for instance, every proton and neutron is made up of 3 smaller particles, and they're quarks, actually, and they're stuck together with this strong nuclear force. So by breaking up protons, you can actually detect these things indirectly.
This is where, particle accelerators come in.
That's right, yeah. So Rutherford's initial experiments with the radioactive atom are now being done at much higher energies in order to delve deeper and deeper into the proton, for instance.
So tell us a bit more about what you're doing. I sort of understand it as you do the maths that then the particle accelerator people try and work out if it's right or not.
Yeah, that's it gets a bit blurred around the edges, and we both do bits of each other's jobs. But that's right. I do a lot of theory. There's a lot of sums. I try and work out models of the early universe to explain facts about the universe that we see today, and then most importantly to work out ways of testing these theories by looking at the data coming out of the experiments.
So this is working out what you should see if you smash 2 particles together?
If the theory is right, yeah.
But why do you want to smash things together? How does that actually help?
Well, it's the only way, because you can't actually see with a naked eye or even with a microscope. You can't see these particles, they're much too small. So the only way to probe them at all is to have something very high energy that breaks them apart, and you can see what they decay into, for instance. You can get a picture of what happens after those collisions, and that's the only way really you have of probing them.
And what's new about the Large Hadron Collider? Because what have we done in the past, and how does this differ?
Yeah, so plenty of different collisions have been happening in the past, and basically the energy gets higher and higher and higher every time. And through Einstein's equation equals mc squared, if you've got more energy, you can make heavier particles. So particles that are previously undiscovered, when you pass a certain energy threshold, all of a sudden you'll be able to produce them, and that's what's hoped, particularly for the Higgs boson, which is a hypothetical particle that's, hopes will show up there.
So up until now, people have been slamming things together the same way as they will do in the LHC, but now they're going to be able to do it even more powerfully.
Yeah, basically that's right. I mean, the technology's come on a lot, and that's why they're able now to do such high energy collisions. But yeah, that's right.
Where's this going to stop? I mean, if we've got this new, exciting, huge particle accelerator, what if you do some sums or find some evidence that means you have to build an even bigger one to get even higher energies? Do you think that the LHC will be the answer to everything?
Not necessarily. You might need to build one more, actually.
An even bigger one.
Yeah, well, it won't necessarily be bigger, but
size
it
of
would
Belgium.
be straight.
Don't these things consume energy on the scale of a national grid just for this one experiment?
It's not as much as that, actually, but it is a lot of power. I mean, it's 100 megawatts or so. So it's a significant.
That's about 20% of a reasonable nuclear power station. So that's quite a lot, isn't it?
Yeah, it's a lot of power. And so you have to weigh up the cost of these things and decide whether the science you're going to get out of them is actually worth the cost. And it was decided, and I think rightly, that for the LHC the answer to that question is yes. And it'll be that decides whether the next one's built.
Thanks, Ben. That's Ben Allenag. In just a second, we're going to talk to Christina Lazzaroni, and she's going to tell us how we're detecting some of those particles that are produced during these big collisions. And if you have any questions for them, email them. chris@thenakedscientist.com.
Sorting out the sparks from the quarks. The Naked Scientists. For more information, get online at nakedscientists.com.
This is The Naked Scientists with Dr. Chris and with Dr. Kat, and we're talking particle physicists, particle physics rather than particle physicists. Christina Lazzaroni is from Birmingham University. Hello, Christina.
Hello.
Now, we've heard from Ben about some of these collisions and the huge energies that are going to be produced, and presumably from those collisions there are particles produced or evidence that particles get produced, so we can try and understand what's inside atoms. So what are you actually looking for in your experiments?
So that's right. We try to collide together in this precise case for the Large Hadron Collider is two protons together, accelerated at about the speed of light. And the fact that they have this huge energy will make possible to produce heavy particles and particles that were never seen otherwise at the very beginning, at the origin of the universe. So that's what we try to find. Essentially, we try to find new particles that we were not able to see before because we didn't have enough energy.
So what you're trying to do is to simulate in a laboratory environment the Big Bang. So how all this energy got turned from a pinpoint source of energy into the stuff, the matter that is the stuff we see around us today.
Yes, that's quite the idea, yes.
I guess the question is, though, is that safe? Are we going to spawn a new universe in CERN, Geneva, where actually, people do say it's the centre of the universe in some respects, but is that a good idea?
Yes, it is actually a very good idea. And no, we are not to destroy the entire universe. But previously, for example, at CERN, we have been smashing particles together for years. In fact, CERN has been celebrating its 50 years quite recently. And nothing of such catastrophe ever happened. And there is good reasons for that. So the idea that we got higher and higher energies because we want somehow to go more and more back in time. So we want to see the particles that were produced more back and back in time. But that doesn't mean that it's dangerous, because this particle lives so shortly and they're not dangerous in itself that there will be no harm for anybody.
How can you ever know that you really have faithfully recreated what was going on at the Big Bang?
Now, that you probably, okay, let's be honest. We would not recreate the exact condition of the Big Bang, but what we want to do is try to go at the very similar condition as much as we can. That doesn't matter the perfect condition, to try to understand how these particles were formed and the new particles that may come over, and try to build a more complete pictures from that.
So, theorising for a minute and sort of straying into Ben's territory. So, what do you think actually happened then? When the universe was first born, there was a lot of energy around. So, could you just talk us through what you think, on paper at least, probably happened?
Right. So, yes, at the very beginning, we think that there was a new state of matter, which called quark, gluon, plasma, which in fact is one of the main topic of one of the experiments at LHC. So, you know that in quarks are confined in protons and neutrons. So, in fact, we never see quarks free so far. We see protons and neutrons, but not the quarks. But we believe that at the very beginning, there was such hot and dense state of matter that the quarks were actually free. And so it's all together some sort of big, hot and dense soup of quark and gluons. So then from there, the thing started to freeze out. And there are models that has to be somehow this kind of sort of studies that we do with gases and with liquid, sort of thing. And so it freezes out, and at some point somehow matters or atoms, as we now believe they're formed, and also light is released and go out forever, and that is what we observe. Then from atoms we got bigger objects and so on.
So when you design an experiment for the LHC, as it will be next year when it switches on, we hope, in CERN,
we hope, yes.
What's going to be happening is a stream of protons is going to be whipping round this circle at 27 kilometres long at nearly the speed of light, tremendously high energy, and that beam will then be brought into collision course with a second beam going the other way.
Yes.
The two will then cannon into each other at a point that presumably you know where that collision will happen. So what are you looking for?
So at that point, in fact, there's going to be 4 places of collisions along the ring. And at that point, we place in these collisions points somehow of huge cameras that take almost sort of photographic pictures of what's going on. So then from these pictures, you try to use some sort of forensic science to go back and see from the traces that they left in the detector what was actually happened in the first collision.
That doesn't sound too complicated. The price tag has been huge. How long are you going to have to do this for to see the kind of evidence that you need to say, now we know what's going on?
Well, it actually depends on particular what people are looking for. If you look for very rare processes, for things that they're very, very rare, you have to look for long, of course. There might be other things that you spot immediately. We hope to see the Higgs boson quite fast, but, you never know until you see it.
And just to finish off, Christina, Ben mentioned it, you've now mentioned it. What actually is the Higgs boson?
Right, so the Higgs boson is supposed to be the thing that gives everybody mass. So it's somehow, we could imagine like a sort of gelatin that fill up the space. And the bigger you are, the bigger resistance this gelatin offers to you. So somehow the Higgs mass is this sort of gelatin that fill up the entire space. Yeah? And somehow we give you mass because it gives you a measure of the resistance that you have going through it.
So this is what Ben tells us should exist, but you're now setting out to try and find whether it does or not.
Yes, if it doesn't exist, in fact, the whole theory needs to be revised quite fundamentally, yes.
Thank you very much. That's Christina Lazzaroni. She's from the University of Birmingham. Thank you very much, Christina.
I'm absolutely fascinated by the Higgs boson. I've heard it called the God particle, the absolute fundamental. Anyway, we can come back to discussion about all those kind of bosons and muons and things later. But now it's time to go to Diana O'Carroll, who has a rather sticky question.
Hello and welcome to Question of the Week on The Naked Scientists. Now, this is one of my favourite questions of the week because of all the practical research I had to do for it.
Hi there, my name's Ian Guest. I'm from Sheffield. Despite being a former physics teacher, I got stuck on a problem, which was, why is it that chocolate chips in cookies melt if you touch them, but they survive the baking process?
But we had another listener write in with a chocolate cooking problem.
Hello, this is Simon Griffiths from Brisbane, Australia. I have an interesting question for the naked scientists. Why don't Cadbury's flakes melt? I've tried microwaving and double boiling with no luck, and I thought it would be a tasty experiment for the naked scientists.
So we have several issues here. One of them is that cooking chocolate has different melting properties to ordinary chocolate.
Hi, my name's Stephen Houston. I'm a food scientist in the School of Life Science at the Heriot-Watt University. And I have to talk about the reasons why chocolate melts at different temperatures. When you make chocolate, you roast the cocoa beans and extract something called chocolate liquor. To make eating chocolate from that, you normally add extra fat, cocoa butter, and that reduces the melting point of the chocolate so that it becomes closer to body temperature, so it melts in your mouth when you eat it. With baking chocolate, you don't add extra fat, and that gives it a higher melting point.
Then there's a special case of the flake.
My name's Paul Bidder. I'm an independent food technologist, and I've spent some time working in the confectionery industry. I think that the explanation for this is that the distribution of fat within the flake type of chocolate is different from normal chocolate. Basically, chocolate is a mixture of very finely ground particles of sugar, cocoa, and milk solids, and that's surrounded by the cocoa butter or cocoa fat. Now, when the cocoa butter melts, if the fat is very well distributed, it allows the fat to lubricate the individual particles, and so they can slide over each other quite easily, and that will give you a nice runny chocolate. If, on the other hand, fat within the chocolate isn't as well distributed, the particles of chocolate won't slide over each other and not then give you a nice runny chocolate. It just happens that in the case of flake, the manufacturing process is slightly different, and the fat is not as well distributed as it would be in the case of ordinary chocolate.
But how do chocolate chips stay chippy in biscuits and cakes?
This is slightly different, I think, from the situation with the flake, in that when chocolate does melt, it doesn't melt in exactly the same way as, say, an ice cube would do if you heat it up. But if you melt chocolate without applying any force to it, it actually tends to retain its shape, and that's because of the structure of all the particles that are there within the matrix of the fat. The biscuit around it provides enough support for the chocolate chip to remain chip shape throughout the baking process.
And why might cooking permanently change chocolate after it has reset?
It may be that during the baking process, the fat distributes itself around within the chocolate chip a little bit more effectively, and so perhaps can melt a little bit easier. A more likely explanation, the fat within the chocolate chip becomes mixed with some of the fat from the biscuit. And when you get two different types of fats mixing together, the actual physical effect is that it reduces the melting point of fat mixture, and that may account for why the chocolate, after it's been baked, appears to melt easier than the uncooked chocolate chip.
So to sum up, don't cook with flakes and watch out for those cocoa fat matrices, because the wrong sort can make you very sticky. Well, next week we'll be exploring all those hidden hairy bits.
Hi, my name is John, and I live in Hong Kong. My question is about pubic hair. Some people have said it is to protect your bit, or to keep your bits warm, or to make you smell more attractive to the opposite sex. I want to know, why do humans have it, and what its function is.
And after that, I'll be finding out where energy gets its energy from.
Hello, my name's Paul Tevendale from Woking. My question concerns the speed of light. If the speed of light is slower in glass than in air, where does the energy come from to speed it up as it exits the glass into air? And why does this not violate the law of conservation of energy?
If you know the purpose of seemingly superfluous hair or a little particle physics, do send your answers and questions to me at questionoftheweek@thenakedscientist.com, or put your thoughts on our forum. That's all for a very well-fed question of the week. Back to you guys.
Oh, thanks, Diana. And I personally think that some experimental evidence is definitely required. So I'll be hitting the chocolate chips, I reckon. The talk of pubic hair is somewhat putting me off. If you know why we have pubic and underarm hair, or how light can speed up as it leaves material without getting extra energy from somewhere else, do email us. It's questionoftheweek, or one word, @thenakedscientists.com.
Fancy listening to The Naked Scientists in your bed, on your way to work, or even at work? Why not subscribe to our podcast? For more information, visit nakedscientists.com/podcast.
Now, this is The Naked Scientist with Dr. Chris and with Dr. Kat, and we were inviting you earlier to take your old-fashioned TV screen, which is the long, deep ones with a cathode ray tube inside, and turn them upside down, see what happens, and also wave a magnet near the screen. Now, Mark is in Bletchley. He's had a go. Hi, Mark.
Hello, Chris.
Welcome to The Naked Scientist. What did you find?
Right, well, I've got a television with the green gone on it. Until I start to turn it on its side, and I'm doing it as I'm speaking now, and I seem to get the normal colours come back.
Maybe you've been watching your telly upside down for years, Mark.
When I actually turn the television set upside down, all I've got is green. Everything is green.
What about the magnet? Have you tried the magnet?
With the magnet, I'll try one of my... I've got I'm a radio, so I've got odd speakers here. It draws the green at one side of the set, and as I move the speaker up the other side, it draws the red gun.
This is because there's a big magnet in your speaker. That's why you're using a speaker, yeah?
That's right.
Yeah. So basically what you're seeing is very funny, colourful effects when you either turn it upside down or when you bring a magnet very close to the screen.
Actually, it looks quite good on its side. I might leave it on its side, Chris.
Mark, we like that. Stay with us. Let's see if you're right. Let's go back to Ben and Dave and find out what happened.
Welcome back to Kitchen Science. I'm still with the 23rd Cambridge Brownies here, and we are going to find out what happens when you turn an old CRT-style monitor upside down. So again, girls, you said earlier you think the screen's going to go fuzzy. Is that right?
Yes, I think it might let out all the particles of the TV.
OK. All right then, Dave. Well, obviously we need somebody who's big and strong to turn this upside down, and we can't ask the Brownies to do it for us. So while Dave turns the screen upside down, I want you girls to tell me if you see anything strange happening.
The colour's fading. It's going all blurry.
Yeah. The print is getting smaller.
And I can see that it's actually gone a little bit green. You're quite right, it has gone a bit blurry, hasn't it? Can you read it now?
Not really, because it's upside down.
Well, even if you do turn your head upside down, can you read it?
No, it's the print's gone all small.
So, Dave, you've shown us that turning a CRT-style TV upside down makes the colours go funny, and it has really lost its focus and gone slightly green. It looks a bit sickly. Is this permanent?
It should be fine. There's two things you could do to solve this. One is to turn it the right way up. The other one is to turn it off and on again.
Now, Dave, you said that we're going to try something with a magnet on the screen. Is that the next thing to do?
Yeah, that's the plan. This is the one which might do some damage to the television, so only do this on an old TV. So, Poppy, here's a very strong magnet. What I want you to do is put it near the screen and see what happens.
The colour seems to fade, and it seems to make sort of a little sort of flowery sort of colour with all these, like a nice little pattern.
It looks like a rainbow, and it's going all wonky. It looks like one of those kaleidoscopes when you turn it.
That really is actually quite beautiful, although I don't think I'd like it then when I was trying to work. It seems to have twisted the image on the screen a little bit as well. Dave, what is actually happening here?
Well, to understand this, you've got to understand how a TV works. Now, at the back of the TV, there's a series of things called electron guns. These fire electrons towards the front screen of your TV. These beams of electrons then scan across the TV in a series of lines, building up a picture.
But I've never seen my TV appearing like from the top corner and scanning across in lines.
On a TV in this country, it will happen about 60 times a second, so your eyes aren't quick enough to notice it. Now, when one of these beams hits the front of the TV, it hits blobs of things called phosphors. When they get hit by the electrons, they get given lots of energy and they give off light. There's different kinds of phosphors for different colours, one for red, one for green, and one for blue.
Oh, right, and so because they're tiny, again, a bit like it scans so quickly I see one picture, they're so tiny that instead of seeing lots of blobs, I see the one colour.
Yeah, that's right.
So why does pointing a magnet at the screen make the colours go all funny?
Well, in the same way that if you put a current through a wire when it's in a magnetic field, it will move like in an electric motor. If you put a magnetic field near some moving electrons, which is an electric current, it will get bent. And that's actually how the scanning is done in the first place, with a series of electromagnets at the back of the TV.
So the electromagnets at the back of the screen bend this beam of electrons to make sure that they hit exactly the right place on the front of the screen.
Yes, and if you add another magnetic field from your magnet, you can then bend them into the wrong place. So quite often the electrons will hit the wrong phosphor and it'll go the wrong colour.
So our magnet just stops them from hitting their target?
Yes.
But what's that got to do with turning the TV upside down? How come that made such a difference?
Because the Earth has a magnetic field, which is why compasses work. The TV is sitting in a magnetic field to start with. So if you turn it upside down, that magnetic field is pointing in a different direction. So it deflects them a little tiny bit and the colours go wrong.
So when we first turn on our TV, it sets it up for the Earth's magnetic field and takes that into account when it aims the electrons. But why did it seem to fix itself when I turned my TV back on?
Inside the TV, there's things called degaussing coils. When it turns on, the TV puts a very strong current backwards and forwards through these coils. This removes any magnetisation in the TV and sets it up perfectly for the way the magnetic field is at the moment.
Seeing as you lot were playing with magnets on my screen, does it look like it used to look now?
No, it looks sort of more wavy.
Are there any patches where the colour has changed?
In the corners mostly there's kind of colours like where there shouldn't be.
Do you think we'll be able to fix this by turning it off and on again?
It's worth a try.
OK then, well, would somebody like to switch it off?
And LRS, do you want to turn it back on again?
It's worked because the colours come back. Yes, they have mostly, but there's one bit of a highlighted sort of bit.
Right, OK, I see. So is it possible that we have done permanent damage to my monitor, Dave?
It's conceivable, but with any luck, turning it on and off a couple more times will fix it for you, Ben.
So this would be why people shouldn't try it at home with a TV that they care about?
Yes.
So how do you feel about the fact that today you've been doing a similar experiment to some of the top scientists in the world?
I feel like I'm a scientist.
Fantastic. And with Kitchen Science, of course, anyone can be a scientist in their own home. So that's all we have for this week. We'll be back with more experiments next week.
Goodbye.
Thank you very much, guys. Absolutely fantastic. You can find out more fabulous experiments and explanations for why they work on our website at nakedscientist.com/kitchen science. And well done, Mark in Bletchley. Well done.
That's okay.
You were absolutely right.
Great.
In your observations. Thank you very much for taking part.
Okay, Chris, all the best.
Thank you. It was great to have you on the show.
Cheers.
And now it's time to wrap up with some particle physics questions. We have a question from David in Portland, Oregon, and he wants to ask Christina. He's heard that scientists could potentially make black holes in the lab. Could we do this, and would it, destroy the universe?
Yes, we would like to make black holes. The Large Hadron Collider would be very interesting because there are lots of things we don't know about them, and we could study them. And no, they would not destroy the entire universe because they would be very, very localized, and they live for such a short time that would not destroy absolutely anything. They're entirely safe.
Why wouldn't they grow and get huge?
Because they will decay and die instantaneously like anything else, so they will not collapse and getting all the stuff.
I'm glad you're so sure. How big's your insurance policy? Now, very quick question for you, Ben. Charles in Buckden says, Hi, unclothed ones. Could there exist white holes as a counterpart to black holes?
They're a theoretical possibility, as you can find out from solving Einstein's equations. But if you actually look into them, you can't really see how they would form. They seem to be unstable. They're like black holes, but stuff comes out of them rather than the other way around.
So they're the sort of reverse.
Yeah,
so would the stuff that came out be antimatter? Because in our universe, all the stuff we can see is matter.
It would be any matter and antimatter. I mean, and light would come out. But I mean, they're unstable, so I don't think they can form.
Well, there you have it. Let's hope he's absolutely right. Well, that's kind of it for us for this week. So thank you very much for lending us your ears and lending us your time. It's been great to have you here and joining in on the programme. I'd like to say a very big thank you to Ben Alanak from Cambridge University and Christina Lazzaroni. She is from Birmingham University, and also our production team at The Naked Scientists, Petra Minch, Ben Balster, Mira Sinthalingham and Diana O'Carroll. Next week, we're back looking at stem cells and cloning, so we'll actually be visiting the lab where people are doing cloning experiments to find out how it works and finding out all about the technology that is chimeric animals. What's that all about? See you next week.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.